Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll study decision trees. Decision trees are non-parametric supervised learning methods that can be used for modeling, classification, as well as regression problems. We will first study binary decision trees in classification setting. Tree-based methods essentially partition the feature space into a set of rectangles or cuboids and then fit a simple model in each one of these partitions. They are conceptually simple yet very powerful. Binary tree splits into two branches at every node. Consider an example of a binary classification problem with 4 features. So here we are trying to decide whether to play tennis or not depending on the climate. So here we have days, and on each of the days we are checking out on outlook, temperature, humidity and wind. All these 4 attributes are categorical attributes. Outlook could be sunny, overcast or rain. Temperature could be hot, mild and cool. Humidity is high and normal, and wind is either weak or strong. And depending on these factors, we basically decide whether to play tennis or not. So the output label is either yes or no. And we have data for 14 different days. So a decision tree for this data set may look something like this. We first check the outlook. If the outlook is overcast, we decide to play tennis. If outlook is sunny, then we check the humidity. If humidity is high, then it's no. And if humidity is normal, we decide to play the tennis. If outlook is rain and if there is a strong wind, there is no point in playing the tennis. But if wind is weak, then yes, we can play the tennis. So this is the decision tree, which is just like if-else conditions, and this decision tree is inferred from the training data. We will study how to infer such decision trees from given training set. So what are important issues here? So we need to decide which attribute to choose for splitting, what should be the splitting criteria, and what tree size will give the optimal solution. These are 3 issues that are central to any tree learning algorithm. We'll study the first tree learning algorithm, which is ID3, which is called iterative dichotomizer, and this is the most basic algorithm for building decision trees. Let's look at the training data for ID3 algorithm. Training data consists of a set of n ordered pairs of a feature vector and label representing examples. We denote it by D. The training data consists of input feature vectors x1, x2 all the way up to xn, along with the corresponding labels which are y1, y2 all the way up to yn. Each example is represented with m different features. For classification problem, yi is an element from the discrete set, and for regression problem, yi is a real number. Let's look at the model. A variety of algorithms have been developed for learning decision trees. Most of the algorithms are variations of a core algorithm known as ID3 algorithm, which is iterative dichotomizer 3. It employs a top-down greedy search through the space of possible decision trees. So what is the model in case of decision trees? Tree itself is a model in case of a decision trees. And there are so many trees that are possible, and we need to find out the tree that is suitable for our training set. So ID3 algorithm employs a top-down and greedy search. ID3 learns decision tree by beginning with the question which attribute should be tested at the root of the tree. To answer this question, each attribute is evaluated with some measures to determine how well it alone classifies the training examples. Let's consider a classification problem with label y and feature x1 and x2. So we have two features x1 and x2, and there are two classes here, the ones which are denoted by color red and the other one which is denoted by color blue. If we split the data set according to feature x1, then we have this particular split where at some value θ1 of x1 we decide to draw a boundary or a threshold, and any value below θ1 goes in region 1, and if it is greater than θ1 it goes to region 2. So we can represent this situation in form of a tree where we are checking on the feature x1. If it is greater than or equal to θ1, we classify it into region R1, and if it is greater than θ1, we classify it into region R2. Next, we decide to break the region R1 into two parts based on some value θ2 of x2. If x2 is less than or equal to θ2, we classify the point into region R3, and if x2 is greater than θ2, we classify the point in region R4. So now we are getting successive axis parallel partitions of the feature space. Right now we have three partitions which are R2, R3 and R4. If we decide to further partition x2 inside R2, we have the following situation. Now we have a value θ3 of x2, and we check in the region R2, we check if x2 is less than or equal to θ2, we send a point or we classify it in the region R5, and if x2 is greater than θ3, we classify the point in the region R6. So we further divide this particular region into two parts by checking on the value of x1 with threshold θ4. So we have one more level added in the decision tree where we check in the region R6 if x1 is less than or equal to θ4, we send a point to region R7, and if it is greater than θ4, we send it to region R8. So the key idea here is to divide the feature space into different partitions such that in each of the partition we have points from the same class as much as possible. So let's try to see how to achieve this particular goal with some systematic mathematical formulas. So that's part of the training process. So the best attribute is selected and used for splitting at the root node of the tree. A descendant of the root node is then created for each possible value of this attribute, and the training examples are assigned to the appropriate descendant. The entire process is then repeated using the training examples associated with each descendant node to select the best attribute for splitting at that point in the tree. This forms a greedy strategy for an acceptable decision tree in which the algorithm never backtracks to reconsider its earlier choices. Let's look at the impurity measures that we use at each node for deciding on the split. If we define Pik to be the proportion of data points in node I or in region Ri with class label k, and this k could take one of the values from k different class labels. So this is basically the proportion or the proportion of points that are labeled with label k. So Ni is the total number of samples in the region, and here this particular expression tells us the points that are labeled with class k, and we sum over this. So this gives us the total number of points with label k, and we divide it by the number of samples in region Ri. That gives us the value of Pik. The second measure that we use is misclassification error. It is a proportion of misclassified examples in node I. So here, let's say k of I is the prediction of class in node I. So we choose the class k which has got maximum pik. That class is assigned to that particular node, and we found out the number of examples that are misclassified by doing 1 minus pik. So this gives us the proportion of misclassified examples in node I. The next measure of impurity is Gini index, and Gini index is calculated as sum of product of pik and 1 minus pik for all k different labels. The fourth measure is entropy, and entropy for node I is given by minus of summation of k equal to 1 to n pik log pik to the base 2. In ID3, the entropy is calculated for each remaining attribute, and the attribute with the smallest entropy is used to split the dataset on this iteration. Then there is next measure, which is information gain, which is based on entropy, and information gain is a measure of the effectiveness of an attribute in classifying the training data. It is simply the expected reduction in the entropy caused by partitioning the examples according to this attribute. So intuitively, the information gain of an attribute or of a feature is calculated as entropy of dataset minus entropy of that attribute or feature. Formally, the information gain, which is Ig of s, a for an attribute or feature A relative to the collection of samples S, is defined as entropy of S, which is entropy of the whole dataset, minus entropy of the attribute. So S is the dataset, A is the attribute or feature, entropy of S is the entropy of the dataset, and this is entropy of attribute. So here what we do is, in order to calculate entropy of the attribute, we perform summation over different values of the attribute, and we take the ratio of number of examples with value v for that attribute divided by the cardinality or total number of examples in the whole dataset into the entropy for SV, which is a subset of the data where the feature A has value v. And we'll see some of the examples of this in the subsequent slides. So in ID3, information gain can be calculated for each remaining attribute. The attribute with the largest information gain is used to split the data on that iteration. Let's also look at what is a stopping criteria. So we keep on building tree level by level, but we need to stop somewhere, and we will look at what are the stopping criteria. So the recursion on a subset of training example may stop in one of these cases. Every element in the subset belongs to the same class. In that case, the node is turned into a leaf node and labeled with the class of the examples. Second condition could be that there are no more attributes to be selected, but the example still do not belong to the same class. That means there is still some amount of impurity in that node. In that case also, the node is made a leaf node and labeled with the most common class of examples in that dataset, in that subset. There are no examples in the subset. That could be the third condition for stopping, and when that happens, there are no examples in the parent set that match the specific value of the selected attribute, and if that also happens, we stop growing the tree in that direction. Let's try to model a tree on the play tennis dataset, and this was our play tennis dataset with 14 different examples. So the first thing is to determine the feature for splitting the data at the root node. For that, we calculate the entropy. So first we calculate the entropy of the whole dataset. So here we have the we have play as our target attribute, which has got two values, yes and no. So there are 14 examples, out of which 9 are positive, that means the target value is yes, and 5 are negative examples, which have got target value of no. The entropy of the dataset S can be calculated as h of S minus 9 by 14. So the first part of the equation is the entropy due to the label yes, and second part is due to label no. So there are 9 out of 14 examples that are positive, so this is the fraction of the positive examples into log of that fraction to the base 2 minus the fraction of the negative examples into log of that fraction to the base 2, and this turns out to be 0.94. So the maximum value of entropy is 1 and the minimum value is 0. So there is a lot of entropy or impurity in the data set based on the targeted label. The next task is to decide how to select the attribute for splitting the tree. So for that we evaluate different features. So let's first evaluate the feature wind. So if we divide samples based on wind, which is either strong or weak, then we have 6 yes and 2 no for the value of wind equal to weak. So the entropy for the value equal to weak is 0.811. So we applied the same formula, or we use the same calculation as we did for calculating entropy of the entire data set. So since 6 out of 8 examples are yes, we have the fraction of positive examples, we multiply that with the log of the fraction to the base 2, and then we sum that up with the fraction of examples with label no multiplied by the log to the base 2 of the same fraction, which is 2 by 8 in this case, and entropy for S weak comes out to be 0.811. For the value of the wind equal to strong, we have 3 yes and 3 no, and this is the condition where there is maximum impurity because there are two classes that are in balance. So whenever that happens, we have the maximum entropy. So since we have 3 out of 6 yeses and 3 out of 6 no's, we have entropy of 1. So we calculated those entropies for S weak and S strong, and we used these values to calculate the information gain for the attribute wind. And the information gain for attribute wind is calculated according to the formula which is listed over here, and we substitute the values, which is h of s, which is entropy of the entire data set, minus entropy for minus the entropy for the value of the wind equal to weak, minus entropy of value of wind equal to strong, and we scale up each of these entropies by the fraction of the number of examples which are yes and which are no to the total number of examples in the data set. So this turns out to be 0.048. So the information gain for attribute wind is 0.048. This means that if we divide a data set by keeping wind attribute as the root, we get reduction of 0.048 in the entropy value. Next, we evaluate the outlook feature. There are 3 values in outlook: sunny, overcast, and rain. We calculate the entropy for sunny, entropy for overcast, and entropy for rain. And you can see that the entropy for sunny is 0.971, as well as rain. Rain also has got the same entropy, which is 0.971. And see, for sunny there are 2 yes and 3 no's. For rain there are 3 yes and 2 no's. So there is just interchange of the terms and we get the same entropy. In case of overcast, we obtain a pure node where there are 4 yes and 0 no's. And since this happens, this is a situation where there is a 0 entropy because all examples belong to the same class. So we obtain these entropies and we have carried over or rewritten these computations from the previous slide, and then we calculate the information gain for outlook, and you can see that the information gain for outlook is 0.46 by substituting respective values of entropies for different values of the outlook. So this means that if we divide the dataset by keeping outlook attribute as the root, we get a reduction of 0.46 in the entropy value. Next, we evaluate the temperature, which again has got three values: cold, mild and hot. S cold has 3 yes and 1 no's, so we have the entropy of S cold is 0.811. For S mild, there are 4 yes and 2 no's, and the entropy of that is 0.918. Then S hot, you can check for S hot, this is yes, then there is yes over here, and for these two hot values there are no's, so it has got 2 yes and 2 no's. So the entropy is 1 because the number of class labels are in equal proportion, so the entropy is 1. So we use these entropies to calculate information gain for temperature. So we substitute the values of the entropy of the whole data set and entropy for each value of the temperature, and we scale the entropy for each value of the temperature by the fraction of examples with that value. So we obtain information gain equal to 0.029. So if you use temperature as the root, we get reduction of 0.029 in the entropy value. Finally, we also evaluate humidity, which has got two values, high and normal. For high, there are 3 yes and 4 no's. So we have the entropy for S high equal to 0.985, and for S normal we have the entropy as 0.593. So you can see that for S high there are 3 yes and 4 no's. So you can check it over here. These two highs, there are 2 no's, then there are 2 s's, then there is another no, so no becomes 3. There are 4 no's and there are 1, 2 and 3 yes for S high. For S normal, you can see that there are 6 yes and 1 no. You can tally it by looking at this particular table, and we obtain these respective entropy values. Now we'll use these entropy values to calculate the information gain for humidity. So the information gain for humidity is 0.151. So if we use humidity at root, we get a reduction of 0.151 in the entropy value. So this is what we got for different features. The information gain for wind was 0.048, for outlook it was 0.246, for temperature it is 0.029, and for humidity it is 0.151. And since the attribute outlook provides the maximum reduction in entropy, we choose it as a root node. Let's look at the decision tree with outlook at the root node. So there are three values of the outlook: sunny, overcast and rain. So we create three subtrees. So one subtree for each value of the outlook. For sunny, we get these examples where outlook is sunny. For overcast, we get 4 examples where outlook is overcast, and we get 5 examples where outlook is rainy. So we have this particular division of the data set of 14 different examples. There are 5 sunny, 5 rainy and 4 overcast rows, which are divided into 3 different separate subtrees or in 3 different regions. We can keep splitting the data in the same manner as we did for the root node, and when we do that, the final tree looks something like this. So we have outlook at the root node, then on the left subtree we have humidity at the root of this left subtree and wind at the root of the right subtree, and then if humidity is high, we assign the value no to play tennis. If humidity is normal, we say yes to play tennis. Then for overcast it is yes. If it is raining and there is a strong wind, then it's no. If it is raining and wind is weak, then it is yes for play tennis. In this video, we studied ID3 as an algorithm for building decision trees. We studied how to split the node based on different impurity measures.